Hello everybody. In this presentation I will talk about nuclear power in Korea, which takes about 30% of Korea's electricity generation and will be expanded to achieve carbon neutrality by year 2050. In Korea, 28 nuclear power plants have been built and operated. The first one was Gori 1, which started operation in 1978. The second one is Walsung Unit 1, except these two units, which are now in permanent shutdown after 40 years of operation. 26 units are currently in operation with a total capacity of 26 gigawatts. Those units are located in 5 sites, which are located in along the eastern and western coast of Korea. Now 4 units are under construction in 2 sites, so that a total of 32 units have been constructed in Korea. This chart shows the construction history of the 32 units for 52 years since 1971. The critical time in the Korean nuclear technology development was in 1987, when a group of nuclear engineers were dispatched to combustion engineering of the United States for the nuclear power plant design technology transfer. At the time, US vendors did not have new contract because of the TMI and Chernobyl accident. So the nuclear technology transfer contract could be made at a relatively cheap price. In 1990s and 2000, 12 Korean standard plants called OPR 1000 were constructed based on the combustion engineering technology. In parallel, the development of APR 1400, which is Korea's unique advanced power reactor, the development has been carried out. 4 units of APR 1400 were constructed in Korea, and 4 units were exported to UAE. And another 4 units are under construction. Here you can see that the construction of 32 nuclear power plants has continued for more than 50 years without any blank year. Thanks to the continuous construction, Korea was able to establish a self-sustaining nuclear power ecosystem with the full technology independence, which became the basis of the efficient and low-cost construction of nuclear power plants. These are the major companies in the nuclear power ecosystem. These 5 companies, including KEPCO, Korea Electric Power Company, are state-owned. Equipment manufacturing and construction are done by private companies like Dusan Airmobility and Hyundai Construction Company. The 28 nuclear power plants have generated about 1/3 of Korea's electricity for the last 45 years. The total nuclear generation was 4.4 trillion kilowatt hours, and the share of nuclear electricity among the total electricity generation reached about 40% until 2005, but it dropped to 23% during the nuclear phase-out period in the previous government. Fortunately, the nuclear share recovered the 30% level in this government. The nuclear power generation cost was able to be kept very low because the construction cost was reasonably cheap thanks to the efficient nuclear power ecosystem, and also because the fuel cost was low. The low-cost nuclear power was the major factor for the cheap electricity price of Korea. It is important to note that the cheap and stable electricity was one of the most important driving factors for Korea's rapid economic and industrial growth. This figure shows the increasing trend of nuclear power generation with the orange line and the income per capita of the Korean people with the blue line. It is clear that the increase in nuclear power generation led the increase in the income in most periods. Surprisingly, Korea's nuclear power development started quite early, thanks to the extraordinary vision of our first president, Dr. Seungman Lee. In 1959, only 6 years later of the termination of the Korean War, the construction of the Triga Mark II research reactor started, along with the establishment of Korea Atomic Energy Research Institute, KARI. In 1987, 44 KARI engineers were dispatched to combustion engineering for the nuclear technology transfer training. I am proud that I was one of the 44 KARI engineers who received the on-the-job training at combustion engineering for 2 years. The continued development of nuclear power technology, including APR 1400, resulted in the Baraka export contract in 2009. Now the 4 Baraka units in UAE are all operational. The on-time, within-budget construction of the Baraka plant demonstrated the excellence of Korea's world-top-class nuclear power technology. Now let me move to the topic of advanced reactor development for carbon neutrality. There are 3 reasons to develop advanced reactors. The first one is to replace coal power plants with highly safe small modular reactors, or SMRs. SMRs are easier to implement innovative safety enhancements concept because they are small. The first one is by component integration. In a large reactor, major components like reactor, steam generator, and pumps are separated and connected through pipes like this. Then there is a potential risk of a pipe leak, which will cause a serious loss of cooling. In SMRs, these components can be integrated into a reactor vessel because each component is small, so that potential leak can be prevented to guarantee higher safety. The second is by passive system. This is the NuScale's Voyager reactor, which does not have a pump. It uses natural circulation to remove heat from the core. The coolant is heated at the core, which is located at the bottom, and the heated coolant moves upward. The heat is extracted at the steam generator located above. The cooled coolant is then moved downward because they are heavier. This is natural circulation. The passive system employing natural circulation is safer than the active system involving pumps, which might not work if there is no electricity in an accident condition. Because SMRs are small, they can be made in a factory and transported to the site for installation like this. Since SMRs have much higher safety, they can be placed at an existing coal power plant site without the need for satisfying strict site restrictions, unlike large nuclear power plants. And by factory-based modular manufacturing and construction, the construction cost can be reduced. The second reason is to generate carbon-free industrial heat. Note that 21% of global carbon dioxide emission comes from industrial combustion. Gas or liquid metal cooled reactors need to be developed to provide carbon-free high temperature heat. The third reason is to produce hydrogen, which is needed for the decarbonization in the transportation sector with the fuel cell cars and trucks. Hydrogen can be generated economically by nuclear electricity and heat. In Korea, KARI is the sole developer of advanced reactors. We are developing both water-cooled and non-water-cooled reactors. SMART is the first water-cooled reactor which was already licensed in 2012. ISMR is an enhanced version of SMART which targets a low generation cost and higher safety. For non-water-cooled reactors, there are three types: sodium fast reactor, gas-cooled reactor GCR, and molten salt reactor MSR. Let me give a brief explanation for each of the 5 SMRs. SMART is an integral type 100 megawatt SMR in which all the major components are integrated within a reactor vessel. Its development started quite early in 1997, and the standard design approval was obtained in 2012. An improved version called SMART 100, which has better passive safety features, was developed as a joint design project with Saudi Arabia in order to use it for the electricity generation and desalination in remote coastal cities. Unfortunately, the demonstration project suffered a delay due to the changes in political environment of both countries. We are now seeking the opportunity to use SMART 100 as the heat source to generate high temperature, high pressure steam for the use in the sand oil extraction in Alberta, Canada. ISMR has innovations over SMART for enhanced safety and economics. There is a steel containment outside the reactor vessel so that potential water leak from the reactor vessel can be contained. And the passive cooling of the reactor is possible with this structure. The generation cost is reduced by increasing the module capacity from 100 to 170 megawatt and by placing 4 modules in one site, so that the total capacity does become 680 megawatts, which is adequate to replace coal power plants. The standard design and verification of ISMR is in progress now, with the objective to acquire the standard design approval by year 2028. KARI had been developing an SFR called PGSFR, which stands for Prototype Generation 4 SFR, for more than 20 years. The development of PGSFR was terminated in the previous government due to the nuclear phase-out policy. Salus is a spin-off design from PGSFR, which targets a longer cycle. The Salus design is currently under technical safety review by IAEA. Currently, the planning of a national project to enhance the flexibility and economics of Salus is going on with the participation of private entities such as NAEK Construction Company. KARI had been working actively on the development of high-temperature gas-cooled reactor, which can provide high-temperature heat needed for the production of hydrogen. A major outcome of the earlier work was the computational tools and modeling technologies, which were later used in the design analysis of USNC's MMR, micro modular reactor. A TRISO fuel particle manufacturing facility was established at a lab scale, and a high temperature helium loop was constructed as well. This loop is being used as the heat source for high-temperature steam electrolysis. The revival of high-temperature gas-cooled reactor development for the industrial heat generation is currently going on as a public-private partnership project. Many companies like POSCO Engineering and Construction and SK Chemical companies are participating in the high-temperature gas-cooled reactor development. Kerry started the development of a molten salt reactor for ship propulsion. The important advantages of molten salt reactors is that the reactor core can be made small and simple because because the fuel is mixed in a molten coolant salt, so it is adequate for ship propulsion. It is expected to be safe because no significant dispersion of radioactive materials is expected due to the solidification after leak in an accident condition. However, it involves technical difficulties associated with the corrosion. The mid-term plan is to finish the basic design and license application by year 2028. Now let me conclude. Continued construction of Sode 2 nuclear power plants for more than 50 years provide the self-sufficient complete nuclear power plant supply system in Korea. It became the base of the efficient and low-cost nuclear power plant construction as proved by the UAE Baraka project. With the R&Ds of various new projects being paralleled by construction, the nuclear power technology in Korea is well established. Now various advanced reactors are under development for different uses in the road to carbon neutrality. SMART is for small electrical grids and resource mining in remote cities. ISMR is primarily to replace coal power plants. Salus is for long-term operation in remote places. And high-temperature gas reactors are for high-temperature industrial heat supply and hydrogen generation. And MSR is for ship propulsion. Thank you for your attention.